North Korea withdrew from the Treaty on the Non-Proliferation of Nuclear Weapons in 2003. It subsequently developed nuclear weapons, with 5 underground nuclear tests culminating in a suspected thermonuclear explosion, a hydrogen bomb, on the 3rd of September 2017. Now a team of scientists, led by Dr. K. M. Srijith of the Space Applications Center, Indian Space Research Organisation, ISRO, have used satellite data to augment measurements of tests on the ground. The researchers find that the most recent test shifted the ground by a few meters, and estimated to be equivalent to 17 times the size of the bomb dropped on Hiroshima in 1945. The new work appears in a paper in Geophysical Journal International, a publication of the Royal Astronomical Society. Conventional detection of nuclear tests relies on seismic measurements, using the networks deployed to monitor earthquakes. But there are no openly available seismic data from stations near this particular test site, meaning that there are big uncertainties in pinpointing the location and size of nuclear explosions taking place there. Dr. Srijith and his team turned to space for a solution. Using data from the ALOS-2 satellite and a technique called synthetic aperture radar interferometry (INSAR), the scientists measured the changes on the surface above the test chamber resulting from the September 2017 explosion, sited at Mount Mantap in the northeast of North Korea. INSAR uses multiple radar images to create maps of deformation over time, and allows direct study of the subsurface processes from space. The new data suggest that the explosion was powerful enough to shift the surface of the mountain above the detonation point by a few meters, and the flank of the peak moved by up to half a meter. Analyzing the INSAR readings in detail reveals that the explosion took place about 540 meters below the summit, about 2.5 kilometers north of the entrance of the tunnel used to access the test chamber. Based on the deformation of the ground, the ISRO team predict that the explosion created a cavity with a radius of 66 meters. It had a yield of between 245 and 271 kilotons, compared with the 15 kilotons of the little boy bomb used in the attack on Hiroshima in 1945. Lead author of the study, Dr. Srijith, commented, "Satellite-based radars are very powerful tools to gauge changes in Earth's surface, and allow us to estimate the location and yield of underground nuclear tests. In conventional seismology, by contrast, the estimations are indirect and depend on the availability of seismic monitoring stations. The present study demonstrates the value of spaceborne INSAR data for measurement of the characteristics of underground nuclear tests, with greater precision than conventional seismic methods." At the moment, though, nuclear explosions are rarely monitored from space due to a lack of data. The team argue that currently operating satellites such as Sentinel-1 and ALOS-2, along with the NASA-ISRO Synthetic Aperture Radar (NISAR) mission, due to launch in 2022, could be used for this purpose. Media contacts Dr. Robert Massey, Royal Astronomical Society. Telephone 440-7292-3979 MOB 440-7802-877-699 Press at ross.ac.uk. Morgan Hollis, Royal Astronomical Society. MOB 440-7802-877-700 Press at ross.ac.uk. Science contacts Dr. K. M. Srijith, Geosciences Division, Space Applications Center, ISRO, Ahmedabad, India. Telephone 917926914136 Srijith81@gmail.com or Ritesh Agrawal, Geosciences Division, Space Applications Center, ISRO, Ahmedabad, India. Telephone 917926914138 Ritesh_Agrawal at sac.isro.gov.in. Rajawat, GHCAG, Space Applications Center, ISRO, Ahmedabad, India. Telephone 917926914018 Rajawat at sac.isro.gov.in. Images and captions. Digital rendering of the Earth observation satellite Sentinel-1. Satellites such as Sentinel-1 and ALOS-2 carry advanced synthetic aperture radars that can provide data to map changing land cover, ground deformation, ice shelves and glaciers, and can be used to help emergency response when disasters such as floods strike, and to support humanitarian relief efforts at times of crisis. Credit ESA, ATG Media Lab license type, top INSAR data in ascending and descending orbits depicting surface deformation associated with the 2017 nuclear test. Bottom, comparison of the source location of the 2017 nuclear test estimated from this study, red star, with other estimations. Topography along profile CD showing the cavity, deformation zone and probable location of tunnel. Note that the sizes of the cavity and deformation zones are exaggerated by 5 times for better visualization. Credit K.M. Srijeev, Space Applications Center, Indian Space Research Organization license type. Further information. The new work appears in Constraints on the Location, Depth and Yield of the 2017 September 3 North Korean Nuclear Test from INSAR Measurements and Modeling, KM. Srijeev, R. Agrawal and A.S. Rajawat, Geophysical Journal International, 2020, 221, doi, 10.1093, GJI, GGZ 451. Notes for editors. The Royal Astronomical Society, RAS, founded in 1820, encourages and promotes the study of astronomy, solar system science, geophysics and closely related branches of science. The RAS organizes scientific meetings, publishes international research in review journals, recognizes outstanding achievements by the award of medals and prizes, maintains an extensive library, supports education through grants and outreach activities and represents UK astronomy nationally and internationally. Its more than 4,400 members, fellows, a third base overseas, include scientific researchers in universities, observatories and laboratories as well as historians of astronomy and others. The RAS accepts papers for its journals based on the principle of peer review, in which fellow experts on the editorial boards accept the paper as worth considering. The Society issues press releases based on a similar principle, but the organizations and scientists concerned have